So, hello, my dear students. Good afternoon. Can you hear me? Can you able to hear my voice? Am I audible and visible? JNV Ramnagar students, am I audible? Let me know the answer in the chat box if I am audible. Okay, good. So let's start with today's session. So we are discussing general organic chemistry, GOC part, and in yesterday's session we have discussed the introduction, representation, classification, nomenclature in both IUPAC and common names we have discussed. Okay. So today we are going to start with isomerism. So coming to the isomerism in organic compounds, isomerism, as we all know, it is classified into two. One is structural isomerism and the other one is stereoisomerism. Okay. So coming to the structural isomerism, we have some divisions. The first classification is chain isomerism. Second is position isomerism. Third is functional group isomerism. Fourth is metamerism. And coming to stereoisomerism, we have geometrical and optical isomerism. Okay. So let's discuss each isomerism one by one. So what is meant by structural isomerism first of all? So the compounds which have the same molecular formula but different structures are called as structural isomerism. Now coming to the chain, so when two or more two compounds have similar molecular formula but different carbon skeleton, then we call those compounds as chain isomers. Okay, so different carbon skeleton. So for example, if we take C5H12, so what is the name of C5H12? Can you give me the name of C5H12, which is an alkane? What is the name of this alkane? If all the carbon atoms are arranged in a straight chain manner, what could be the correct name for this compound? It is pentane. Okay, so it is pentane. So here we have 5 carbon and 12 hydrogen. And the other one is isopentane. In isopentane, we have one branch. So here is the branch, okay, with 4 carbon atoms in the straight chain. And coming to neopentane, we have 2 branches. We have 2 branches. Got it? The IUPAC name of isopentane is 2-methylbutane and the IUPAC name of neopentane is 2,2-dimethylpropane. Okay. So in the pentane, we have 5 carbons arranged in a straight chain manner. In 2-methylbutane, we have 1 branch, and in 2,2-dimethylpropane, we have 2 branches. So here you can find that molecular formula remains same, but structure, the carbon skeleton differs. So it is an example for chain isomerism. Okay. Shall I move on to the next isomerism, position isomerism? Shall I? So do you have any doubt from chain isomer? Ramnagar students, do you have any doubt from chain isomerism? Shall I move on to the next isomerism? Yes or no? Yes or no? Am I audible? Am I audible? Okay. So the next isomerism is position isomerism. So when two or more compounds differ in the position of substituent or functional group of the carbon skeleton. Sorry, my dear student, sorry. So coming to position isomerism, so when two or more compounds differ in the position of substituent or functional group on the carbon skeleton, then we call those isomerism as position isomerism. Okay. So for example, C5, C3H8O. So let's take this formula. So here the first compound that I can draw for this is propan 1-ol. Okay, so OH is the alcohol and that OH is attached to the first carbon. So the numbering has to be done from right to left. So 1, 2, 3. So propan 1-ol. And here it is propan 2-ol. So you can find that the position of the functional group is differing. In the first compound, it is 1, and in the second compound, it is 2. So that's why we call this type of compound as position isomerism. Okay, position of the functional group or the substituent on the carbon skeleton differs. Okay, then coming to the functional isomerism. So here two or more compounds having the same molecular formula but different functional group. Here the functional group itself will differ for the two compounds. Okay, so let's take an example. C3H6O. So C3H6O. So the first compound that I can draw for this formula is propanone. Okay, it is propanone. So in the propanone compound, we have the ketone group as the functional group. Okay, then coming to the next compound, which is propanal. So here the functional group is aldehyde. So but the formula remains same, which has 3 carbon and 6 hydrogen and 1 oxygen, but functional group is differing. Okay, so these two are the examples for functional isomerism. Okay, so ketone always pairs with aldehyde. So like this, we have 5 pairs, sets of pairs. I'll give you those pairs. So alcohol always pairs with ether. Okay, the formula for alcohol is ROH, right? So CH3, CH2, CH2, OH. So this is the alcohol. And coming to ether, we have ROR. So CH3O, CH2, CH3. So this is an ether. So in these two compounds, you can see that the formula remains same. That is C3H 5, 6, 7, H8 and O. So this is the formula, but functional group differs. Okay, alcohol always pairs with ether. Then coming to the next pair, which we have already known, that is aldehyde and ketone. So aldehyde formula is RCHO and ketone is RC-O-R. Okay. Then the third pair is cyanide and isocyanide. So the formula for cyanide is RCN and the formula for isocyanide is RHC. Formula for isocyanide is RNC. Okay. Then the next pair is acid and ester. So the formula for acid is RCOOH and for ester it is RCOOR. Okay. So the next pair is alkene and cycloalkene. Alkene means I'll take propene as an example for you, which has CH3, CH double bond, CH2 formula, and cyclic system can be cyclopropane, which has CH2, CH2, and CH2 structure. Okay, clear? So in these two compounds, we have 3 carbon and 6 hydrogen. Okay, so likewise for acid also we can give an example. Like you can take our CH3, CH2 as an example for our group. And here, if you can take RS, first RS CH3 and the second RS CH3. Okay, so both R groups, you can take it as CH3. So finally, in both the compounds, we will have 3 carbon, 7 hydrogen, 6 hydrogen, right? It is not 7. It is 6 hydrogen, C3, 6 hydrogen and 2 oxygen. Got it? So do any of you need any other example for any of the types given here? As all the 5 types given here is clear to all of you? Any doubt? Any doubt guys have? Plus 20. What is plus 20, my dear? Third one. Okay, for third one also I will give. For third one, okay, for cyanide, I will take CH3CN. Okay, but for isocyanide, it is CH3NC. That's all. Very easy. So here carbon is bonded with carbon and here nitrogen is bonded with carbon. That's all. Clear? Any other doubt? Any other doubt? Naresh, you have said some plus 20. What it is? What it is, my dear? Yeah. Okay. Okay, fine. So here functional isomerism is getting over. Shall I move on to the next isomerism? What is the fourth type of isomerism? It is, sorry, yeah, sure. No issues, my dear, no issues, Naresh. So let me move on to the fourth type of isomerism under structural isomerism, which is called as metamerism. Okay, so metamerism is the fourth classification of structural isomerism. Now, so metamerism arises due to different number of carbon atoms on either side of functional group or heteroatom in the molecule. Okay, so let me take an example. C4H10O is an example. So here is the first structure and here is the second structure for this formula C4H10O. Okay, if you see to this formula, the functional group present here, functional group in both the compound is ether. Okay, so ether is ROR, right, or ROR dash. Okay, it can be anything. So this is ether. So both the compounds are having same functional group, but the alkyl groups means this R group. Alkyl groups which are attached to this functional group, they are differing. They are differing. So in the first molecule, the first R group is methyl. Second R group is propyl. Since we have 3 carbon, it is propyl. But in the second compound, both the alkyl groups are ethyl. Both are C2H5. So it arises due to different number of carbon atom. So here we have only 1 carbon and here we have 3 carbon. But here 2 carbon, here also 2 carbon. Okay. So different number of carbon atom on either side of the functional group or heteroatom. Heteroatom is nothing but the oxygen here. Any other atoms other than carbon, they are called as heteroatom. Got it? So the general formula looks like this. So we have a functional group at the center and 2 alkyl groups will be attached with that functional group. And in one compound, both the R groups can be same and in the other compound, 2 R groups may be differing from each other. Okay. So let's see some more example. So ether is an example. And if an ether has to exhibit this metamerism, minimum 4 carbon is required. Because with 3 carbon, you cannot draw the metamer. Okay, if I take with 3 carbon like CH3O, C2H, CH2CH3. So in this compound, we have 3 carbon, right? One is methyl and the other one is ethyl. So if I shift this, what I will get? I will get the same compound. CH3, CH2O, CH, the same compound I will get. So this one is ethyl again and this is methyl. Both are same. Both are methoxyethane only. Okay, so minimum 4 carbon is required to draw the metamerism. Okay, so not only ether, we have amine also. Secondary amines. For secondary amines also minimum 4 carbon is required. Thioether and ketone. So for ketone, minimum 5 carbon is required to draw the isomeric pair. Got it? So any doubt from the 4 structural isomerism? Chain, position, functional metamerism? Do any of you have any doubt from these 4 isomerism? No doubt. So we will move on to the next second classification of isomerism, which is called as stereoisomerism. Okay. So the compounds that have the same constitution and sequence of covalent bonds but differ in relative position of the atom or groups in space. Simply to say, okay, compounds having same molecular formula but a different spatial arrangement of atoms. They differ in the spatial arrangement of atoms. Okay, so they are called as stereoisomerism. So it is all again classified into two: geometrical and optical isomerism. Geometrical isomerism is otherwise called as cis-trans isomerism. Okay, it is otherwise called as cis-trans isomerism. So what is meant by cis and what is meant by trans? So let me take an example and explain that with you. Okay, so but 2-ene I am taking as an example to explain this geometrical isomerism. So what is but 2-ene? CH3, CH, double bond CH, single bond CH3. So 1, 2, 3, and 4. So double bond is between carbon number 2 and carbon number 3. So this is but 2-ene. Okay. Now, so this is called as cis-butene. So why it is called as cis-butene? Because this two alkyl groups are attached on the same side of the functional group. The two alkyl groups are attached to the same side of this double bond. So that's why it is called as cis-alkene. And in the second compound, you see in the trans, you see two alkyl groups or the two similar groups are attached on the opposite side of the double bond. So it is called as trans. It is called as trans. Got it? So this is called as geometrical isomerism. So very easy. So any doubt from geometrical isomerism? So from but 2-ene onwards only geometrical isomerism starts. For but 1-ene, for propene, for ethene and all, you cannot draw the geometrical isomerism. Because in ethene, all the four hydrogen will be same. At least two groups should differ. Then only we can draw cis-trans isomerism. Okay. So any doubt from this? Shall I move on to the optical isomerism? Shall I move on to the optical isomerism? Yes? Okay. So, conditions for a compound to be optically active. So, there are two conditions. If a compound has to be optically active, it has to follow two conditions. One is the compound must have at least one asymmetric carbon. Asymmetric carbon is otherwise called as chiral carbon. Now, what is a chiral carbon? A carbon which is attached to four different atoms or groups are called as chiral carbon. Okay, so here you see I have a carbon at the center and I'm calling that carbon as a chiral carbon because it is joined by four different atoms or groups. We have A, B, C, D. Four of them are different from each other. They are not equal. A is not equal to B, not equal to C, and not equal to D. Okay. So if a compound contains chiral carbon like this, then we can close our eyes and say that the given compound is optically active. Okay. The central carbon is optically active. So this is the first criteria. Okay. One more example. So lactic acid is taken as an example here for you. So in this lactic acid, you see center in the center I have a carbon and that carbon is attached with four different groups. One is hydrogen, the other one is CH3, third is OH, fourth one is COOH. Okay, so it possesses the optically active center. Sorry, just give me a second. And the second criteria is the compound must have non-superimposable mirror image relationship. All chiral carbon containing compounds will have non-superimposable mirror image relationship. What is meant by non-superimposable? Suppose if I'm taking the mirror image of this compound, what I will get? C, H. So COOH will come to this side and here I have OH and in this side I have CH3. Now take this compound and try to superimpose over this first compound. Try to place the second compound over the first compound. So this particular COOH will be placed above the CH3, right? So CH3 is placed above this COOH. So here the vertical part remains same, but the horizontal groups, they will not be superimposed over the other. So they are having non-superimposable mirror image relationship. Okay. So the compound which possess this criteria, they are optically active. Got it? So any doubt from this? So any doubt from the optical isomerism? Students? You have any doubt from the optical isomerism? No doubt? Okay, good. Okay. So let me move on with the, okay, I'll explain yoga. So if a compound has to exhibit optical isomerism, it should follow two criteria. Okay. First criteria is the compound should contain a chiral carbon. Now, what is a chiral carbon? A carbon which is attached to four different atoms or four different groups are called as chiral carbons. Okay. Now, here I have taken lactic acid. You want me to explain the second point? Okay. Um, okay, I'll explain. You take your hand. Okay. This is my first hand. Okay. This is my left hand actually. Now, if I take the mirror image of this hand, I will get this hand. No, this is the mirror. This hand, my right hand is the mirror image of this left hand. Okay. Now, this is the mirror image. This hand is the mirror image. Now, I am just placing this mirror image over the original image. I'm just placing this mirror image over the original image. Okay. Now, you tell me whether my mirror image has been superimposed over the original image or not. Yes or no? It has been superimposed or it has not been superimposed. Others also can reply. What do you say? Superimposed or it is having non-superimposable relationship? Students, tell me. Any of you can give me the answer. All of you can take part. What do you guys say? So this is the one hand. If I take the mirror image of this hand, I will get this. Now I'm going to place this hand over this hand. Tell me whether my both the hands are having superimposable relationship or non-superimposable relationship. What is meant by superimposable first of all? What is meant by superimposable? Yeah, it is non-superimposable because if it has been superimposed, then I should not see these two fingers. So by these two fingers, I can say that my right hand is not being superimposed over the left hand. The image which is below the above image should not seen. You should not see the image which is placed below. Okay, means it has been superimposed. Here, I can clearly say that this is having a non-superimposable mirror image because of these two fingers. Okay, clear? Now, if I take a ball, and if I take the mirror image for this ball, what I will get? I will get the same ball, right? Now, if I try to take this ball and keep above this ball, will you be able to see the ball which is below? If you are looking from the front, obviously no, right? If it is no, then these two compounds are having superimposable relationship. If it is having superimposable relationship, then it is optically inactive. It is optically inactive. But when I take my hand and if I take the mirror image of that and try to superimpose over it, it is not getting superimposed because of these two fingers. Okay. So my hand is having optically active relationship. It is having non-superimposable mirror image relationship. So is this clear for yoga or still you have doubt? Okay. So the next topic is reagents in organic chemistry. So what are the reagents we use in all the lessons of organic chemistry? So they are very, very important reagent. They are electrophiles and nucleophiles. Now, what is an electrophile? What is an electrophile? Electro means electron. Phile means loving. So electron loving species are called as electrophile. Electron loving species are called as electrophile. And they are electron deficient. That's why they are loving the electron. That's why they are seeking the electron. Okay. Since they are very deficient, electron deficient species, they are seeking the electrons. Got it? So electrophiles are classified into three. One is charged. Yeah, it is classified into two, not three, it is two. So charged electrophile and electron deficient electrophiles. Okay, or charged electrophile and neutral electrophiles, I can say. It is charged and neutral. So all the positively charged species, you can see all the alkyl groups. R plus means CH3 plus, Br plus, Cl plus, NO2 plus, NO plus. All these compounds are having positive charge in it. So they are positively charged electrophiles. Electron deficient species are mostly positively charged. Okay. Then coming to the neutral electrophiles. Okay, neutral electrophiles, all electron deficient compounds will fall under this. Now, if I take this BH3, BH3 is an electrophile. Why it is called as an electrophile? Because of this boron. Why? Because of boron. Boron is having empty p orbital, okay, which is empty. So it is electron deficient in nature. So it is acting as an electrophile. Got it? AlCl3, BCl3. So all group 13 elements. All these are boron, aluminium. They belong to group 13. Okay. And aldehyde, ketone. So all of them. In aldehyde, if you see R, C double bond O, H. And here R, C double bond O, R. So here these two centers are called as electrophilic center. Okay, electrophilic center. So this is an electrophile. Then coming to nucleophile, nucleus loving species are called as nucleophiles. And they are electron rich also. They are electron rich compounds. Okay, lone pair or pi electron cloud will be there for nucleophiles. So let's see some example. So nucleophiles are classified into charged nucleophile, lone pair containing nucleophile, and pi electron cloud containing nucleophile. Okay, so three categories are coming under this nucleophile. So in charged, since they are electron rich species, negatively charged species will fall under this category. So Cl minus, OH minus, Amin, HSO4 minus, they are all falling in this. And the compounds containing lone pair, H2O. So in H2O, we have oxygen, and oxygen has two lone pairs. And because of those two lone pairs, it is acting as an electron-rich species. And through this lone pair, it is forming the bond with the other atom. It is donating its electron. Okay. And NH3. Nitrogen have one lone pair here. And coming to ROH alcohol, here oxygen has two lone pair. And here if you go for amine, here nitrogen is there. Nitrogen is having one lone pair. Okay. And coming to the next third category, pi electron cloud containing nucleophile. So here pi bond we have no, in double bond one is sigma and the other one is pi. In triple bond one is sigma, the remaining two are pi. So the pi electron cloud will act as an electron rich center through which it can form the bond with the other. Got it? So these three are the categories of nucleophiles. So any doubt from electrophiles and nucleophiles? Is this clear? Do any of you have any doubt from the reagents, two reagents from electrophile and nucleophile? No? Okay. So now let's move on to breaking of bonds. Okay, let's move on to the next topic called breaking of bonds. So bond breaking is of two types. Okay, one is called as homolytic cleavage or homolytic breakage. The other one is called as heterolytic cleavage. So now what is meant by homolytic cleavage of bonds? Let me take a molecule. Okay, atom A is bonded with its same atom A. Now in this bond we have two electrons. Each covalent bond contains two electrons, right? So this bond also contains two electrons, and one electron is going to the first atom and the second electron is going to the second atom A. Okay, and now they, yeah, very good, Hema Sundar. It is electron equally distributed. So equal electron shifting will happen and each atom will have one electron each. Okay. Now here, if you see the electron movement, it is shown by a curved half-headed arrow, like a fish hook. Okay. So that represents that a single-headed arrow represents that only one electron is moving towards that particular atom. Got it? Now, each species is having one electron each, right? So one electron containing species are called as, very good, they are called as free radicals. Very good, they are free radicals. So here radicals are formed. Very good, students. Radicals are formed. Now how do we know that this particular molecule will will give radical? How do you know? How can we find out that this particular molecule will form only the radicals? How do you identify? By seeing the thing which is given above the arrow mark. Okay. So this type of homolytic cleavage of bond is initiated by radiation. That is using light energy or by heat energy. So if you find any H nu kind of thing present above this arrow, like H nu or some heating symbol, okay, light energy, yeah, and also very good. Electronegativity difference is also zero. Okay, in that case also they lead to the formation of free radical, and also in case of this light energy and heat energy, they form this radical. Okay, and also peroxide. And if peroxide is there like H2O2, hydrogen peroxide, C6H5, uh, C6H5 benzoyl peroxide, okay, C6H5 twice and O2, benzoyl peroxide. So this type of COO2. So benzoyl peroxide, this type of molecules will also lead to the formation of radical. And if you heat above 500 Kelvin, it will also lead to the formation of radical. Okay, this is about the homolytic cleavage. And in heterolytic cleavage, if you see, two atoms are bonded. Now, very good, Hemasundar. Two atoms are bonded, but atom A is different from atom B. So, if both are different atoms, then electronegativity difference will also be there. Okay, one atom will be more electronegative than the other. Suppose, for example, if I am taking atom B is having high electronegativity value compared to A, then two electrons which is shared between A and B, they will move towards the atom B. Okay, since B is more electronegative, what is meant by electronegativity? The tendency of attracting the shared pair of electrons towards itself is called as electronegativity. Now I am saying that atom B is more electronegative, means both the electrons which is there in that bond will be pulled towards atom B. So you see here, two electrons are going towards B and B minus A plus I am getting. A is losing its electron, so it is getting positive charge, and B is taking that electron, so it is B minus. So electron movement is shown by curved arrow here, and here cation and anions are formed. So ions are formed from heterolytic cleavage of bond. So it is initiated by polar solvent like H2O. Okay, plus minus giving compounds are called as polar solvent, or by intense heat also you can get this type of intermediate. Okay. So here one is positively charged and the other one is negatively charged. Now, yeah, electrolytic cleavage is due to electronegativity difference between the bond atoms. Yeah, that's what I have said, my dear. Good. So, so far we have seen three intermediates forming. One is free radical, and here one is positively charged, and the other one is negatively charged species. So these three species which has single electron, which is positively charged and which is negatively charged, these three species are called as reaction intermediates. These three species are called as reaction intermediates, and now we are going to discuss in detail about this reaction intermediates. Okay, so do any of you have any doubt from the breakage of bond from heterolytic and homolytic cleavage? Is everything clear up to this? Shall I start with the reaction intermediates? Yes or no? Okay. So coming to reaction intermediates, so there are three intermediates. One is free radical, the other one is called as carbocation, third is called as carbanion. Okay, if a carbon is carrying positive charge, it is carbocation. If a carbon is carrying negative charge, it is called as carbanion. Okay, then coming to free radical, single electron containing species. If a carbon is having only one electron, it is called as free radical. Suppose if I am having CH3 dot like this, CH3 dot, this is called a CH3 with a single electron in the carbon, then it is called as a free radical. Okay, so here homolytic it is formed by the homolytic cleavage of bond, right? And if you talk about the neutrality, so it is actually electrically neutral. Free radicals are electrically neutral. They will not conduct any electricity. Okay, so it is having one unpaired electron in the p orbital, and it is highly unstable. All the three intermediates are highly unstable in nature. Okay, they unstable in the sense they are more reactive. Okay, they will not remain in the stable form for long. So they will immediately react with the other compound and they will lead to some other product. So all the three intermediates are highly unstable, or I can say it is more reactive in nature. Okay, and if I want to talk about the hybridization of this carbon, of this radical carbon, it is sp2 hybridized. Okay, sp2 hybridized systems have trigonal planar geometry, and that geometry is seen here. So you can see that geometry, CH3. Okay, so all the sp2 hybridized system will have trigonal planar geometry, and around this carbon, if you check, so 1, 2, 3, 4, 5, 6, and this is the seventh electron. So around this carbon, we have 7 electrons. So actually, how many electrons should be there around an atom? We should have at least 8 electrons, right? So then only we can say that particular compound is exhibiting the octet. Okay, each atom should exhibit the octet configuration. So to attain that octet configuration, minimum, not minimum, 8 electrons is required. But instead of 8, here we have only 7 electrons. Here we have only 7 electrons, and that's why we call the free radicals as electron deficient compounds. They are called as electron deficient intermediate because as it requires only 1 electron, so it is not considered as a Lewis acid. Only one, very few, only 1 electron is required, no? So it is not considered as a Lewis acid. So Lewis acid means electron. More electron deficient species are called as Lewis acid. And here only 1 electron is required to attain the octet. So it is not considered as the Lewis acid. So these are the very important points which you have to note down under free radicals. So any doubt from this? Shall I move on to the second intermediate, which is carbocation? See students, if I'm going very fast, just stop me. Okay. So the speed is okay for you, right? We have already discussed these things in detail in the class. So since we are going in a crash course kind of manner, I'm going very fast. Okay. So if you're getting any doubt in between, put your doubt in the chat box. Okay. I will see to your doubt and I will clear that. So far everything is clear to all of you guys. I think so. Thank you, Naresh. So now we will move on with the, yeah. Highly unstable means now they are in the high energy state. That is the meaning. Okay, only the stable compounds will have the low energy. So I have already told you, no. So in the thermodynamics lesson also we have discussed stability. Stability is inversely proportional to the energy. So this is the relation. So this is the relation which is applicable to all type of system. So highly unstable. So stability is very less, unstable. They are not more stable. They are least stable. Okay, means the energy is high. Energy is high. They are the high energy species. Okay. If they come to the lower energy, they will automatically attain more stability. Got it? Got it, students? Yeah. Okay, Stephen. So the next is carbocation. So carbon, if a carbon is bearing positive charge in it, then we call that as carbocation. So CH3 plus is called as carbocation here. So it is formed by the heterolytic cleavage of bond. It is a positively charged compound. Okay. And here we have an empty p orbital. Yeah. It is highly unstable again. Since it is also an intermediate, it is highly unstable. Very good, Divyanush. It is sp2 hybridized like free radical, and it is electron deficient like free radical, but it acts as an Lewis acid as well as an electrophile. Okay. Radicals were not considered to be a Lewis acid, but here it is considered as a Lewis acid. Why? Around this carbon, we have 3 bonds, and each bond contains 2 electrons. And here around this carbon, we have only 6 electrons. How many electrons we have? Only 6 electrons. So 2 more electrons are required to reach the octet configuration. Okay, so that's why it is acting as a Lewis acid as well as an electrophile. Electrophile means electron deficient compound, positively charged electrophile. Okay, clear? This is about the carbocation. Hybridization, stability, everything is same as that of free radical. The only thing is it acts as a Lewis acid, that's all. Okay. Lewis acid means, while discussing the equilibrium, I have might have told you. Lewis acid means electron deficient species. Lewis acid means electron deficient. Lewis is a scientist. Lewis is the name of the scientist, and he gave the definition for acid and base. Okay, according to his definition, acids are the compounds which are electron deficient in nature, or the electron acceptor, electron acceptor, electron pair. Okay, electron pair acceptors are called as Lewis acids. Electron pair acceptors are called as Lewis acids. Okay. So since the CH3 can able to accept the electron from the other species, it is called as a Lewis acid. For example, BCl3, AlCl3. Now we have seen, no. So boron can accept the electron, aluminum can accept the electron through, using its p or empty p orbital. So they can accept the electron from the other species. So they are called as Lewis acids. So like BCl3 and AlCl3, CH3 plus is also acting as a Lewis acid. Clear now? Clear? Shall I go on with carbanion? Yeah. Now coming to carbanion, okay students. So the negatively charged species are called as, no issues Naresh, no issues. So the negatively charged species are called as carbanion. So it is also formed by the heterolytic cleavage of bond. Okay. So what is the formula here? CH3 minus. And it is a negatively charged compound with it is having one lone pair in its hybridized orbital, and it is also highly unstable. Divyanush is giving me the correct hybridization for all the intermediates. Very good, very good. No, no, it is not SP, it is SP3. It is SP3, Naresh. So SP3 hybridized. SP3 hybridized means the structure will be, yeah, tetrahedral. It is tetrahedral. You can see the tetrahedral arrangement of three hydrogen atom and one lone pair. So it is tetrahedral in nature, and it is electron rich. It is electron rich, and it acts as a Lewis base. What is Lewis base? Electron pair donor. Electron rich compounds are called as Lewis bases. Okay, and also it acts as a nucleophile. Nucleophiles are negatively charged species. So CH3 minus is acting as a nucleophile. Okay, clear? So these are the informations about free radical, carbocation, and carbanion. Now we are going to see the relative stabilities of these three intermediates. Okay, so first I am taking a free radical. Okay, so I have a methyl free radical at first, and if I replace one of this hydrogen by an alkyl group, I will get RCH2 dot, and this is called as primary free radical. This is called as a primary free radical. And if I replace the second hydrogen also with another R group, then it is called as secondary free radical. Then if I replace the third hydrogen also with another R group, it is called as tertiary free radical. Okay, primary, secondary, tertiary. Now if I compare all these four, tertiary free radicals are more stable compared to secondary, primary and methyl. Okay, so the same order is followed for carbocation also. Okay, same order is followed. Tertiary is more stable for free radical and carbocation. Okay, only for carbanion, it is just the opposite. The methyl carbanion will be more stable. Then comes our primary, then comes secondary, then comes tertiary. Clear? Yeah, due to inductive and hyperconjugative effects. So these two effects I will be discussing in the next session. So it will come under electronic displacement effects. So because of those two effects only, this particular intermediate, these three intermediates are following this order. So in that part also, I will explain this in detail. Very good, Naresh. Your answer is correct. So the intermediates are following this order because of the reason that you have given. Very good. So, any doubt? Any doubt from the intermediates and its stability for any of you? Is everything clear for all of you guys? Is everything okay? Clear. So, here I would like to close the today's session here. So, in tomorrow's session, we can go with the electronic displacement effects. Okay, inductive effect, resonance effect, hyperconjugation. Okay, and electromeric effect. So, those things we will discuss in the next session. So, here I am ending the class here for you. So, today we have discussed isomerism. Okay, the complete isomerism part we have discussed, and the breaking of bonds, the two different types of breaking of bonds we have discussed. And thirdly, we have studied about the three intermediates. Okay, so try to solve questions on these topics. So see you all in the next session. Thank you so much for listening the today's class. Okay, so if you're having any doubt, you can ask me now. Otherwise, all of us can meet up in the next session. Any doubt? Okay. Okay, then. Thank you, students. Bye bye. Take care. Yeah, thank you.